Okay, we're on lesson 6.1 on antiderivatives, indefinite integrals, and simple differential equations. So the main point of this unit of this section is to teach you how to read this symbol right here. This symbol is called an integral. So integral is really long, skinny S like this, and typically there's a function right next to it, and then there's a beginning and end point. Very, very similar to a notation you had before, which is a summation, sigma notation. Functions right here. Here's where you start, here's where you end. So they are very, very similar, and they actually have very similar properties that they are going to do for us, right? So another way to look at integral is to remind yourself that it is really the process of taking the antiderivative. So taking the derivative backwards. You're going back to what it was before before you take the derivative, right? So if you recall looking at these functions here, what was the derivative? Who had the derivative cosine? Oh, it was sine. So that's why the antiderivative is sine. But don't forget that there's always a possibility of a constant that you can add to these functions. Therefore, we address that by putting a plus c there. C is a constant, because anytime you take a derivative, that constant just goes away, right? Same thing, whose derivative was a positive sign? Well, a cosine will give you a negative sign. So in order for that sign to be positive, you need the original function to be a negative cosine plus c. All right, so these are kind of the simple, basic trig functions that we have here. And make note that you don't have a single secant yet, right? You have secant and tangent, or secant squared. You have a cosecant squared or a cosecant and cotangent, but you don't have a single cosecant or single secant, nor do you have a tangent or a cotangent. Those will come a little bit later once you have more tools under your belt for anti-differentiation. Keep in mind that 1 over x is natural log of x. E to the x is e to the x, very nice, plus c. And your inverse trig functions over here. And then most importantly, your power rule right here. This is our bread and butter for a bit of our lessons here, because we're not teaching the tools yet, right? So right now the most basic idea is the power rule. So when we had power rule in derivatives, we took the derivative and we drop it down. So we're multiplying it with the terms, and then we subtract 1 from the power. So now you got to do it backwards. You got to add the 1 to the power, and then instead of multiplying, you're dividing by that new power. That's how this power rule comes about. Okay, all right. Another idea to look at is this. I am asking you to take the derivative of this function, so equals something, right? So take the derivative, and then I ask you to take the antiderivative of it, basically canceling that action of taking the derivative. That's why you get the same exact equation f of x back, but because you're taking the integral, you have a constant, the possibility of a constant. Now, vice versa. If I ask you to take the integral of this, I'm asking you to take the antiderivative of that, so you're going backwards to what it was before. But then I ask you to take the derivative of it, so you go back to the derivative, so hence you have your original function f of x here. So if it's integral of the derivative, you have a constant, but if it's derivative of the integral, you don't have a constant, okay? For a lot of these, you want to take out the coefficient to put it in the front to multiply, because it actually makes your equation much easier to tackle. You can deal with the coefficient much later, especially if the coefficient's like pi over 6 or 3 pi over 12, 3 pi over 17, something kind of gross, right? The last 2 bullet points are to remind you that just like limits and just like derivatives, we can add our functions, we can combine them, or we can subtract them and split it into 2 separate integrals. These are totally fine, okay? All right, so let's take a look at what tools do I have under my belt. First one is a very straightforward power rule, right? So we go ahead and take this. The antiderivative of this will be 9, that's your coefficient. Your power now is t cubed over 3, 3 is my new power, right? Minus 4t squared over 2 plus 3t, don't forget your constant right here. The act of taking the antiderivative actually, in a way, cancels these 2 things out. It kind of gets rid of it, right? So those 2 things tell you to take the antiderivative. That's why in the next step, they're gone. Now, I do want you to clean this up. You'll get 3t cubed minus 2t squared plus 3t plus c. You could get really, really good out of this, and you could essentially skip the middle step there and just go ahead and reduce out your fractions. But if you need to, it's okay to show your work this way, okay? All right, number 2, how do I deal with something like this? Well, first thing I'm going to do is I'm going to rewrite this because it's not very friendly. So if I rewrite this integral into z to the negative 3 power minus z to the negative 2 power dz, then I can do this using power rule, right? So go ahead and take the power rule. So my function now becomes z to the negative 2 over negative 2 minus 3z to the negative 1 over negative 1 plus c. right? And then you want to clean this up. So ideally, you want to clean this up so it's negative 2z squared plus 3 over z plus c. You really want to try to rewrite it back into a fraction because if we need to evaluate it, it's actually much easier to evaluate as a fraction rather than a negative exponent, okay? What do I do in something like this? Well, when you have a product here, we don't have the tools yet. So the best way to tackle this is to actually multiply this whole thing out, expand it out. So you have the integral of 9x squared minus 6x plus 1 dx. And now I can take the antiderivative. So when I take the antiderivative, I get 9x cubed over 3 minus 6x squared over 2 plus 1x plus c. Right. Clean this up. 3x cubed minus 3x squared plus x plus c will be your final answer. Okay. All right, next problem, similar idea. You have x cubed minus 1 over x minus 1. So the way to approach this, there's a couple of methods you can, but the idea is that you want to divide this out. This is a division problem. You want to divide this out. So you could divide out by using synthetic division. You can divide out using long division. You can also divide it out by factoring. So really up to you, whichever one you're most comfortable with. If you recognize that this is x cubed minus 1 cubed, you can remind yourself that this is really x minus 1, x squared plus x plus 1 all over x minus 1. Hence, reducing out the x minus 1s, your new integral is x squared plus x plus 1 dx. And then now taking the antiderivative, I get x cubed over 3 plus x squared over 2 plus x plus c. And so you got to start getting comfortable with these because most of the time our integrals are going to come out with fractions like this, and we're going to be asked to evaluate with certain values plug into the x. So we got to get comfortable with adding and subtracting fractions. Okay. All right. I know we say not to manipulate, but in this case, if you manipulate, it actually is a lot better to work with. So if you manipulate this into 7, cosecant x is really a reciprocal of sine x, so it becomes 7 sine x dx. And if you want to take this 7 out, it's fine, or you can leave it inside, but this becomes negative 7 cosine of x plus c. And that will be your final answer. That's your original equation. Same thing here. I do want to remind you that there is an identity you can use. 1 plus cotangent squared actually should be replaced with something, right? So if you recall in trig, you have sine squared x plus cosine squared x equals 1. The Pythagorean identities will allow you to replace 1 plus cotangent squared into cosecant squared z. And then you have your cotangent z over cosecant z, right? So the identity allows me to do that replacement. And then algebra allows me to reduce these out. So you have cosecant z, cotangent z, dz, which is much more doable because your equation becomes negative cosecant z plus c. Okay. All right, next one. Similarly, we want to rewrite this so it's something doable, but I think the first step would be to look at it and say, can I change secant w? Secant w is 1 over cosine, so for me that doesn't do much change. Then I look at the alternative. I look at sine w over cosine w. This becomes secant w, tangent w, right, dw. So now you know then that the antiderivative is secant w plus c. Okay, we move into this idea where our integral really, in a way, cancels out the action of taking a derivative. So when I look at this, I look at this piece first. I'm being asked to take the derivative of this function right here. It's something. I'm not going to do it because it's wasting my time to do it. Because in the next step, I'm taking the antiderivative. So this antiderivative cancels out the action of the derivative. Hence, I have the same function as I had before, but because I was asked to take the integral, I have a constant possibility there. So make sure you address that. Okay. So all these plus c is kind of annoying. I really want to know what the c is, right? So given more information, given some initial conditions, you're actually able to figure out what the c is with all these extra information, right? So the notation of this is to write your f prime, right? 12x squared minus 6x plus 1. And then the act of taking the integral helps me find the antiderivative, so it helps me go backwards. So you take the antiderivative, and you can do these a little quicker now. 12x squared now becomes 12x cubed over 3. So it's 4x cubed minus 3x squared plus x plus c equals f of x. This is your original function because I went backwards. I went from f prime now going backwards to get f. Now I can plug in all the things I know. F of x equals 5 when x equals 1. So all the x's are 1, right? So 4 times 1 cubed minus 3 times 1 squared plus 1 plus c equals 5. Okay, so 4 minus 3 plus 1 plus c equals 5. So 2 plus c equals 5, c equals 3. So don't forget to plug it back in. It is never okay to just write c equals. You gotta write the equation. So f of x equals 4x cubed minus 3x squared plus x plus 3. Okay, and that's what we're solving for. So anytime it says solve the differential equation, what it means is give me the original function. Give me the y equals or the f of x equals. All right, number 10, the notation is slightly different. So the only extra step you need to do is make sure you separate your variables. You have your dx over here as a fraction. You got to multiply it over. So it becomes dy equals 4x to the 1/2 power dx. That way, when I take the antiderivative on both sides, I can take the antiderivative according to the variable it is deriving with respect to. So on the left-hand side here, this becomes a y. And yes, there's a c that's involved in here. It's a plus c on this side. But remind yourself that there's also a plus c on the x side. So we don't need both constants because if you combine those constants, it's still a constant. So mathematicians realize that, oh, you really just need one constant on the right-hand side, which is where the x is, right? So on the right-hand side, you have 4x to the, add 1 to your power, that's 3 over 2. You got to divide by this new power, which is essentially is multiplying by the reciprocal, right? And then put your c here. This is where the constant goes. Okay, I'm going to clean this up a bit. Okay, and in place of the x and y, I'm going to replace my initial condition. Y equals 21 if x equals 4. So I'm going to put 2 squared in there because it's a lot easier to work with that way. So I get 21 equals 8 times 8 over 3 times 8 plus c. So I'm going to change the 21 to 63 over 3. 64 over 3 plus c. C is negative 1/3. So my final answer is y equals 8 over 3, x to 3/2 minus 1/3. That's your final answer for your function. Okay, now we are giving you the second derivative. We're going to work backwards 2 times to find the original function. All right, so again, same notation. You put the d squared y equals 3 sine x minus 4 cosine x dx squared. The act of taking the antiderivative will get rid of one of these dy dx's. Hence, you have dy equals, now let's take the antiderivative. 3 sine of x, the antiderivative of sine x is cosine, so negative 3 cosine x minus 4, the antiderivative of cosine x is positive sine x, plus c, put your dx here. Now, to plug it in, you actually have to put the dx back with the dy over dx, that's your y prime, right? And then now you can plug in your first initial condition. Y prime equals 2 if x equals 0. So 2 equals 0, plugging in zeros here. So it equals negative 3 cosine of 0 minus 4 sine of 0 plus c. That gives me 2 equals negative 3. This is 0 plus c. C equals 5. So going back to this equation, because that's what I'm going to use next. Negative 3 cosine x minus 4 sine x plus 5, put the 5 in, dx. Now I'm going to take the antiderivative one more time to get my y function, my original function. So y equals negative 3, antiderivative cosine is sine x, minus 4 cosine x, so plus 4 cosine x. Sorry, the antiderivative of sine x is cosine. The antiderivative of sine x is negative cosine x, so we have a negative sine x here, hence it comes out as a positive cosine x, right? Plus 5x, and some books like to call this plus d, because they don't want you to confuse, oh, the c from before and c from now. I don't have a preference. I usually just put plus c here, but I'm going to follow the book for now, okay? All right, more initial condition here. It says y equals 7 when x equals 0. All right, so y equals 7 when x equals 0. Okay, let's see what that looks like. So negative 3 sine of 0 plus 4 cosine of 0 plus 5 times 0 plus d. All right, sine of 0 is 0, 5 times 0 is 0, but 4 times cosine of 0 is actually cosine of 0 is 1. Don't forget that. So 7 equals 4 plus d. equals 3. So final answer is y equals negative 3 sine x plus 4 cosine x plus 5x plus 3. That is your final answer. And the beauty of this section is that now you can actually check your work. You can take the derivative of this and take it one more time, see if it matches the original problem of the second derivative. Same thing with all these integral functions. If you take the derivative, right? If you take the derivative, you can see if it comes back to the original equation for the most part. Some of these, because we clean it up, so it doesn't match the original functions perfectly, but it'll match the cleaned up version of the function. Okay. All right, last one. I give you f double prime equals 4x minus 1. So you're going to start with the double prime, 4x minus 1, and you're going to take the antiderivative. You're going to take the integral, okay? Because that will give me my f prime. So that gives me f prime equals 2x squared minus x plus c. So now my initial condition says f prime of 2 equals negative 2. So negative 2 equals 2. So 2 times 2 squared minus 2 plus c. So negative 2 equals 8 minus 2 plus c. Negative 2 equals 6 plus c. So c equals negative 8. Okay. Now my f prime is 2x squared minus x minus 8. Okay. Now I'm going to take that and do one more antiderivative because this is f prime and I want f. So take the antiderivative, and that would give me f of x equals 2x cubed over 3 minus x squared over 2 minus 8x plus d. So now it says f of 1 equals 3, right? So then my initial condition is 3 and 1 plugged in to every single x. So 3 equals 2 times 2 over 3. 2 times 1 cubed over 3 minus 1 squared over 2 minus 8 times 1 plus d. So 3 equals 2/3 minus 1/2 minus 8 plus d. Now it's just a lot of fraction work. So this gives me 4 minus 3 is 1/6 minus 8 plus d. So 18 over 6 equals 48 negative 47 over 6 plus d. Equals 65 over 6. So f of x equals 2x cubed over 3 minus x squared over 2 minus 8x plus 35 over 6 would be your final answer for this problem. Okay, all right, that's it.